Studies in the early 1900s in quantum theory served to revolutionize our understanding of the basic particles of matter. We had known for some time that atoms were the basic building blocks of matter, but the idea of subatomic particles was just beginning to emerge. In the 1890s, J.J. Thomson proposed his plum pudding model of the atom. Plum pudding is decidedly English dessert that has dried fruit suspended randomly throughout. Think along the lines of a blueberry muffin and you get the same idea. Thomson proposed that the structure of the atom was similar to plum pudding in that the atom consisted of a homogeneous positively charged sphere with tiny negatively charged electrons moving around inside it. These negative charges were called electrons. Going back to the idea of the plum pudding, the whole pudding can be considered positive, while the plums can be thought of as the electrons. In 1911, Ernest Rutherford conducted an experiment that tested the idea of Thomson's model. Rutherford's experiment bombarded a very, very thin sheet of gold metal with positively charged alpha particles, and looked to see what kinds of patterns were formed by the deflection of the particles. Since the plum pudding model assumed that there was no concentrated area of positive charges, we would expect to see the positive alpha particles pass through the gold foil with no problem. Alpha particles are very large compared to electrons, so any collisions would be more of a mowing over of the electrons by the alpha particles, and there would be very little deflection. For a visual on this, imagine taking a cannonball and shooting it at a piece of tissue paper. Most of the alpha particles passed through the gold foil undisturbed. However, there were a few that went off in different directions at large angles, and some that even bounced back and hit the screen in front of the foil. The alpha particles passing through unchanged suggests that there's a lot of empty space. But the wide deflection of the positively charged alpha particles indicate that there must be some small concentrated regions of positive charge within the foil. Based on this information, Rutherford proposed his planetary model of the atom. Just like planets orbit around the sun, he put forth the idea that tiny negatively charged particles orbit around a larger, dense, positively charged nucleus. He was correct in arguing that an atom consisted of mostly empty space, but there were a few things about his model that turned out to be incorrect. First, the model cannot explain why individual atoms produce discrete spectra of visible light. If electrons are accelerating in orbit around the atom, then we should see a wide range of electromagnetic frequencies. Line spectra is something we will discuss in more detail shortly. Second, according to Maxwell's theory of electromagnetism, an electron accelerating in a circular orbit would be giving off energy in the form of light. Giving off energy should result in a decrease in the kinetic energy of the electron, decreasing the velocity along with it. Losing velocity would result in the electrons not being able to stay in orbit around the nucleus and crashing into the nucleus. Since we know that atoms are generally stable and, well, still around, we know that this cannot be true.